Okay, Chapter 6, Section 1 is about well-mixed mixtures called solutions, suspensions, and colloids. Okay, so a well-mixed mixture is a solution, and if you recall from Chapter 1, a mixture is when two or more things are in the same space. You are not creating a new compound. There are no chemical reactions. So the three main forms of solutions are called pure solutions, suspensions, and colloids. A pure solution means you can't see the individual particles. They have the same properties throughout. The particles cannot just settle out and they do not pass through a filter. So the only way to separate the two parts of the solution is to let the water, which is the solvent, evaporate to leave the solute. A suspension is the second type of solution. Particles can be seen. They're very large. They can be separated either through filtration or just letting them settle. So if there's a solution, you're going to get a different amount of solute and solvent in every mouthful that you try. A colloid is the third type of solution. These are mixtures where the particles are undissolved. They cannot settle out. The particles are larger than in a pure solution, but smaller than a suspension. The only way we can identify we have a colloid, since you cannot filter out, evaporate, or any kind of filtration, is using what's called the Tyndall effect. And that is where a light beam goes through, but instead of going straight through, the light beam bounces off every individual particle, so it kind of glows. Now, the two parts of a solution are called the solute and the solvent. The solvent is the largest amount of whatever part of the solution it is. It's what is doing the dissolving. The solute is the smaller amount. It is what is getting dissolved. Water is known as the universal solvent because it is a polar covalent bond, meaning it has an unequal sharing of electrons, giving it that partial positive and partial negative charge to it. That means any kind of ionic compound will dissolve and break into separate ions, and anything else that is a polar covalent compound will also dissolve in water. These are all different types of solutions. You do not need to know these for the test. There is no memorization needed. Now, when particles are in solution, remember, let's use water as our example. If it's an ionic compound, like salt, table salt, sodium chloride, it's going to break apart into its separate ions. If you notice here, sodium has this positive charge. It's a positive ion. So the oxygen end of the water molecule will surround it. It's not attaching. It's not making a compound. Every individual sodium ion would get surrounded by the oxygen end of the water molecule. The chlorine ion, because it's got negative charge, would be surrounded by the hydrogen parts of the water molecules. Again, they're not combining, they're not making a new compound, they're just surrounding. Each and every one of these parts of the crystal here, they're each individual ions, and each one would be surrounded by the appropriate part of the water molecule. Molecular solids are those things that are using a covalent compound. They're sharing electrons, so they're neutral atoms sharing electrons to be a neutral molecule. When they break down to their smallest molecular compound, they're still neutral, so the water would surround it any old way. It would not be any specific part. When we look at what happens when a solute is added to a solvent, it changes the freezing point and boiling point. It's going to lower the freezing point, meaning the temperature at which that solvent freezes would be colder than normal. So if you look at this winter time, we add salt to the roads to break up the ice, meaning for the water to be in an ice form, it has to be colder than its normal temperature. It also raises the boiling point. Evaporation and boiling are two different types of boiling or vaporization. Sorry, I couldn't think of the term there for a second. Evaporation takes place at the surface. Boiling takes place below the surface. They're both types of vaporization. When we add a solute to the solvent, we're going to raise that temperature, making it hotter than it normally is for boiling to happen. So this is why you add salt to a pot of water if you're going to make pasta. Instead of water boiling at 100 degrees Celsius, now it might be 105 degrees. It will take longer to reach the boiling point, but once it starts boiling at that hotter temperature, food will cook faster. All right, the review questions. The 3 ways to tell the difference between a pure solution and a suspension. Do the particles settle out or not? If they settle out, it's a suspension because they do not settle out in a solution. Are the particles visible? If the particles are visible, it's a suspension. If they are not visible, it's a pure solution. And then will the particles pass through a filter? If they do, it's a suspension. If they do not, it's a pure solution. When you look at sugar molecules and salt breaking apart into their smallest component, remember that salt breaks into its ions, and each ion gets surrounded by the part of the water molecule that is an opposite charge. Sugar molecules are neutral, so the water molecules surround each molecule of sugar, but they will not be based on the partial charge of the water molecule. Salt is sprinkled on roads, again, because it's going to lower the freezing point, making any ice that's on the roads convert back to a liquid form before it gets cold enough to refreeze. And then the temperature needs to be lower for ocean water to freeze because there's salt in it, whereas normal water would freeze at 0 degrees Celsius. That's why lakes get ice on them. It takes a lot colder temperature to get ice water to freeze or ocean water to freeze.